All right, we're going to continue on with our classwork from night number 12. We're going to do problem 5 and 6, and that's all in this lecture, so it'll probably be about 10 minutes. So our problem number 5 says using function notation, find, it should say an equation, find an equation to represent the total cost in dollars of a certain number of tickets that sell for $15 per ticket. After you have found a function, use function notation to find the total value of 10 tickets. So I've started by writing down the information. That's called our setup. So I've given my function our name, using function notation. I've called it T of X, meaning the total dollar of X tickets. And that's going to be found using the total value formula, being the number of tickets times the dollars per ticket. And again, the X being the number of tickets, and the value of our tickets is going to be $15. So we are going to start out by writing our formula. So T of X, oops, not T of 0, T of X is equal to, and T of X is going to be equal to the number of tickets, which I don't know, X times the value per ticket, which is 15. So there's our very simple formula. Remember that the total value formula is just another expression of a linear equation, which doesn't have a baseline. Now for the second part, what we wanted to find is the value of 10 tickets. So 10 is our X, so that would be T of 10. And in order to find the value of 10 tickets, remember that we're doing an evaluation problem. So we're going to plug in 10 for X, and remember that multiplying by factors of 10 just adds the 0, so that's 150. And of course, these are dollars. So that's problem number 5. Now moving on to problem number 6. Problem number 6 is a little bit more difficult of a problem. I did some tricky little things in giving you this problem. So it says employment at Disneyland in years since 2005 can be modeled using a linear function. Let the function e of x represent the number of employees in thousands of x years since 2005. So the two tricky things in this are that the years since 2005 and that our employees are represented in thousands. So I'm going to call our E of X the number of employees in thousands, and X is our years since 2005. So we're given the information in part A that the fact that 2008 there were 21,200 employees, and in 2010 there were 22,000 employees. And this means that in 2008 it was 3 years since 2005, and 21,200 is 21.2 thousand, right? The units being in thousands. And 2010, that's 5 years since 2005. And 22,000 means 22 thousandths. So now from there I can write ordered pairs, right? And remember, back in chapter 1, chapter 2 time frame, we learned to just pick off the dependents and the independents and write those down, and that's the part of our setup. And then we are actually figuring out which of the independents and which are independent and which are dependent from a story. So we know that our independent is 3 years here, and our dependent is 21.2. And then from the second part of the story, our independent is 5, and our dependent is 22. So from there, we know 2 ordered pairs, and therefore we can find the slope, or the rate of change for this problem. And we're going to be actually using it as a rate of change, but we'll write it like it looks for our slope formula. So you take y2 minus y1, and you're putting that over x2 minus x1. And so when we do that, we're going to get 0.8 in the numerator, and we're going to get 2 in the denominator, and that's going to give us 0.4, and that's our rate of change per year, okay, since 2005. Now from there, we know the slope, but we don't know the y-intercept. Neither of these independents is 0, so we don't know the y-intercept, so we have to use the point slope formula. So we have y minus, and we get to choose one of these ordered pairs to use. I'm going to use pardon me, I'm going to use this one right here. And this is my y1 then, and this of course will be my x1. So my y1, I'm going to put that in there, 22, is equal to my slope, 0.4, and then times x, and then minus my x1, which is 5. And so now I'll have my distributive property. So we have y minus 22 is equal to 0.4x, and then 0.4 times 5, that will give us just simply 2. And then finally, I'm going to add 22 to both sides to solve this for y, putting it in my slope-intercept form. And when I do that, I'm going to get y equals, and that will be 0.4x and 0.4x, and then that'll be plus 20, and that'll be my equation in point and slope-intercept form. So from there, I can write it as E of x, the number of employees, x years from 2005 can be represented as 0.4x plus 20. Pardon me. And now we're ready to go on to the next question. So part B says, predict the number of employees in the year 2012. So 2012, the first thing that we have to figure out is how many years since 2005. Well, that's 7 years since 2005. So what we're being asked to find here is we're being asked to find E of 7. And so once we put it in those terms, we see, oh yeah, it's just a substitution problem. So 0.4 times 7, and then plus 20. And so this is going to give us 2.8 right here. 28, right, with one decimal, 2.8 plus 20, which is 22.8. And what this is 22.8 thousand employees, or 22,800 employees. And that's in 2012. So there we go. And there would be our final answer for part B. And if we wanted to give it in thousands, we could leave it as 22.8 thousands. But I'm sure you're more comfortable seeing it as 22,800. Now the next one says, interpret the meaning of the slope in this model. Well, the slope is the rate of change of the dependent for each increment of the independent when it's written as a decimal like that. So what this means is that we have a change of 0.4, and that's the dependence units, right? So 1,000 employees and it should actually say more employees, right? Because that's what it means, right? It's increasing, it's a positive number, so it's increasing. So 0.4 thousand more employees every year since 2005. And another way of course putting this is 0.4, and that's times 1,000, right? And so 0.4 times 1,000 gives us 4 with 3 zeros and 1 decimal, so it is 400 employees. So another way we could say it is 400 more employees every year since 2005. Now part D says interpret the meaning of f of 0. Well, the first thing that we want to remember is that f of 0, that's letting x equal 0 when y, and finding out what y is. Well, f of 0, therefore, must be my y-intercept. And remember that our y-intercept is our baseline. So when there's no value of the independent, what is the dependent? So we're talking about how many thousands of employees there are at the baseline, the starting point, which is 2005. So we say there's 20,000. So there were 20,000, and I'll just write that as a number so that we don't get confused, 20,000 employees in 2005. And that's our interpretation of the y-intercept, which is what f of 0 represents. And that probably should have really said e of 0 there, because that's what we're talking about in our model. And so those are the real world application problems that we've been talking about over several chapters. Okay, now in the next video I will start up with problem number 7 and possibly get through 4 problems in the next one. I just knew that this was going to be a little bit more extensive and wanted to break it into pieces.